The good news is you get given the equations for time dilation and length contraction. The bad news is you've got to be able to actually use them. And so I'm just going to take you through a couple of worked examples that show you how it can be done. So first one is to calculate the dilated time t dash observed by a stationary observer or an astronaut traveling at 2.8 times 10 to the power 8 meters per second and boils an egg with a proper time of 3 minutes, which is obviously the time on the spacecraft. So I've put in here speed, proper time, and dilated time. You don't need to put the words in. The main thing is you've got v equals 2.8 times 10 to the power 8, t equals 3 minutes, and it's t dash that you're looking for. So always writing down what you know and what you don't know. Then the equation, you'll get a mark for choosing the right equation. And then the numbers into the equation. So you'll get another mark for correct substitution. And make sure you've got the times and speeds the right way around. And from then on, it's just a case of putting that into your calculator and really, make good use of the either the memory function or probably the brackets functions on your calculator. So it's definitely 3 divided by square root, open brackets, 1 minus brackets, v squared over c squared, close your 2 brackets, and it should give you an answer of 8.36 minutes. Next one, a little bit trickier this time. You've got a sample of thorium traveling at 1.5 times 10 to the power 8 appears to have a half-life of 27.7 when observed by a researcher. So that's the dilated time that you've been given. And then you want to try and find out the actual half-life, the proper time. Okay, so that's what we know and what we don't know. Formula again. And then we put the numbers into the formula. So you've got 27.7 hours. And it's t that you're trying to find. And there's your speed in there. So you then rearrange that, so you multiply both sides by that Lorentz term there, and so you have 27.7 times that square root of 1 minus v squared over c squared. That's what you put in your calculator, and that should give you a time of 24 hours. The last one is the trickiest one, where you're trying to find the speed that it would give you the particular time dilation effect. So if we say that a human heartbeat is roughly 0.75 seconds, which is 80 beats per minute, which is an average adult resting heart rate. If mission control were recording that as only 60 beats per minute, in other words, a dilated heartbeat of 1.0 seconds, what would be the speed? So what you know and what you don't know, dilated time, proper time, you're after the speed. Same equation, and this time you're putting in the dilated time and the proper time. There's v that you're trying to find, right in the heart of this pretty complex equation. You can't rearrange that easily just as it is. So I'm going to take you through how you can get to what v squared is and therefore get your answer. First thing is to rearrange the equation so you've got your t and divide it by t, the dilated time. So divided both sides by 1.0 and multiplied both sides by that Lorentz function. There's still v squared. We want v squared on its own on one side of the equation, so we've still got some rearranging to do. Because you've got a square root here, you square both sides, which means that the 0.75 over 1.0 also has to be squared, and we're still trying to get at this. For that, the easiest thing at this point is to just calculate that v squared over c squared, get it as a number, and then subtract it from 1. It's so much easier than trying to rearrange the rest of the equation. So 0.75 over 1, square that is 0.5625. You subtract that from 1 there, and that's equal to v squared over c squared. To get v squared, you take that, which is actually 0.4375, multiply it by c squared, so you've got that's now what v squared is equal to. To get v, you're going to need to take the square root, so all that lot there is 3.9375 times 10 to the power 16. I'm keeping 5 significant figures just to make sure I don't have any rounding errors here. And then finally, get your answer, 1.98 times 10 to the power 8 meters per second. So you will need to practice these. This is much more a sort of AB grade style calculation at higher.